This video is on nucleophilic substitution. So you need to know that nucleophilic substitution is a reaction where one functional group is substituted for another. You need to know about the nucleophilic substitution reaction for haloalkane molecules. So this is a equation showing the mechanism, the overall equation for the mechanism. So you've got here a haloalkane, so this could be chloroethane, bromoethane, iodomethane. So X is just representing Le halogen. And then we've got a nucleophile. So this could be a number of different things. Could be something like ammonia, could be a hydroxide ion. It can have a negative charge, it can not have a negative charge. And what happens in the reaction is you can see that the nucleophile, or the halide, is substituted for the nucleophile. So they swap positions. So the nucleophile is now attached onto the alkane chain, alkyl chain, and the halogen, the halide, it leaves as a negative ion, leaves as a halide. So halogen leaves as a halide. Okay, so here's our haloalkane. So it could be, as I said, chloroethane. The halide, halogen here, halogens are generally very electronegative. So things like chlorine, fluorine especially, very electronegative. So what that means is electronegativity is the power of an atom to withdraw electron density towards itself in a covalent bond. So what that means is that covalent bond, the halogen draws the electron density towards itself. Because it's drawing these electrons towards itself, it gains this partial negative charge. So we draw that looking like this. We say that's delta negative. It's not negative, not completely negative. It doesn't have a negative charge. It's got a partial negative charge because it's drawing some of the electrons away from carbon because it's more electronegative than carbon. Now, because carbon's having some of its electrons drawn away from it, it gains a partial positive charge. So we've got this set up, we've got this polar bond, a partial positive side and a partial negative side. This polar bond is why haloalkanes are open to attack via nucleophilic substitution. It's why they react via nucleophilic substitution, because they have this partially positive carbon. Because you have your nucleophile, so the definition of a nucleophile is something that has a lone pair of electrons that it can donate. So a nucleophile is any species, so species is just a general term for molecules, atoms, ion, any species that can donate an electron pair. So you've got your nucleophile here, and what happens? Well, it's attracted, because it's got this negative, these two electrons, they're attracted to the partially positive carbon. So what we do is we draw a curly arrow. So a curly arrow looks like this, coming from the center of the electron pair, going towards the partially positive carbon. So it has to go towards this carbon attached to the haloalkane, because that's the one which has got a partial positive charge, coming directly from the center of the lone pair. Now this blue arrow is called a curly arrow, that's the official word for it. And what a curly arrow shows is the movement of a pair of electrons. And in this case, we're forming a dative covalent bond between the nucleophile and the carbon. So this curly arrow is showing a covalent bond, or dative covalent bond, to the carbon, to the nucleophile. It's dative because both the electrons are coming from the nucleophile. So one more time, curly arrow shows the movement of a pair of electrons. Okay, so we've got this new covalent bond between the carbon and the nucleophile. So that means the carbon has now got 5 things that it's bonded to. It's bonded to the other carbon, 2 hydrogens, and the halogen, and the nucleophile. It's bonded to 5 things. Now, carbon can't be bonded to 5 things, so one of these bonds is going to have to break. The one that breaks is the carbon-halogen bond. And the way we show that is we show another curly arrow coming from the center of the carbon-halogen bond, curling round and going towards the halogen, going towards the substance which is going to leave. The reason it's this bond that breaks is because the halogen is more electronegative than the carbon, so it's pulling those electrons towards itself already. So it doesn't take much more energy for it to pull them completely and actually to steal it. So both those electrons have now gone onto the halogen. So the halogen has gained its electron, plus it's gained carbon's electron. So it's gained an extra electron, in a sense. So that's why it's going to gain a negative charge. I'm going to draw now what is formed. So we can see what's formed now. The nucleophile is now attached to the carbon, so it has replaced the halogen, so it's substituted the halogen. The halogen is left, taking one of its electrons and one of carbon's electrons, forming a negative halide ion. And we draw the two electrons that it's gained. Well, it's gained its electron from the bond and carbon's electron. So we draw those on it, showing the lone pair on it. It might have other lone pairs, but we just draw this one on there. You can see that the nucleophile, it had a negative charge, but because it formed a dative covalent bond with the carbon, it donated one of its electrons to the carbon, in a sense. So its negative charge has been removed because it's sort of given away one of its electrons. So that is the basics of nucleophilic substitution. It's probably one of the easiest mechanisms. There's one complication we'll go over in a sec. We'll go through some examples. So here is the overall equation for the reaction between bromoethane and the hydroxide ion, forming ethanol and the bromide ion. So the hydroxide ion you can't get a bottle of hydroxide ions, so what we'd generally get is we'd get some sodium hydroxide. I didn't draw the sodium in here because it doesn't take part in the reaction, it just sort of sits in solution. But this would be sodium hydroxide, and actually if you removed all the sort of solution, you'd end up with some sodium bromide ion, so sodium bromide compound formed. Okay, so you've got your bromoethane, and you draw on your partial charges because bromine's more electronegative than carbon, so it gains a partially negative charge. Carbon's gains a partial positive charge because the electrons are being drawn towards bromine. You've got your nucleophile, which in this case is the hydroxide ion. So you've got a lone pair which sit on the oxygen. It must be on the oxygen, not on the hydrogen, because they exist on the oxygen. It's got a negative charge. So what happens? The nucleophile, the hydroxide ion, the electrons are attracted to the partially positive carbon, and they form a covalent bond between the carbon and the hydroxide ion. We show that using a curly arrow coming from the center of the lone pair going towards the carbon. This means that carbon now has 5 bonds, so it's now attached to 5 things. So that doesn't work, so something has to break. So the bond that breaks is the carbon-bromine bond. So that breaks as shown by this curly arrow, so both the electrons go towards the bromine. So here we can see what's made. We can see the ethanol made. So you can see that the OH, the hydroxide, has replaced the bromine, substituted it. And the bromide has left. We draw the 2 electrons because it's gained its electron plus carbon's electrons. We draw that lone pair, and it's got a negative charge. I mean, in reality, if you think about it, bromide's actually got 4 lone pairs, but we don't need to draw those, just those 2, showing that, because you're showing where the electrons on this curly arrow, where have they gone to, that's why you do it. So there's one complication with nucleophilic substitution. I mean, the rest of the nucleophiles are pretty straightforward. I haven't shown you the cyanide ion adding on, but it follows the same patterns as the other one. This is the only one which differs. So this is when ammonia adds on. It's a bit more complex, and the exam board loved asking about it, so it's definitely one you need to know. So the overall equation, you'll notice you've got the same, we'll start off with the same haloalkane, so bromoethane, and we'll add our nucleophile. Things to notice first are that the nucleophile this time doesn't have a negative charge, so nucleophiles do not need a negative charge, they just need a lone pair of electrons. The lone pair happens to be on the nitrogen. You'll notice we've got 2 of them. When we do the mechanism, you'll see why that is, but only one of them actually adds on. So we end up forming this primary amine, so this would be called ethyl amine. You're not expected to name amines AS, you would be expected to at A2, however they will still give you questions that look like this, they just won't ask you to name this thing, they'll give you the name. But this is called ethylamine. You can see that the bromine has left as bromide, so it's gained a negative charge, that's just normal. But this is abnormal. You can see that this ammonium ion is formed as well. So let's go through the mechanism and have a look at why this works. So, first thing to draw when you're drawing these mechanisms, we draw out the haloalkane, put on the partial charges, so partially negative bromine, partially positive carbon. You don't actually get marks for putting the partial charges on, but it helps to visualize what's going on. So you can see you've got a nucleophile. Oh, I forgot to mention, so a nucleophile, the way this word came about, so nucleophile, nucleo sounds like nucleus, phile is the Latin word to like, so nucleophile means likes nucleuses. Nucleuses are positive, so nucleophiles are attracted to areas of positive charge. So I'll draw on the lone pair on the nitrogen, so it's got a lone pair of electrons on the nitrogen. Now we'll show the nucleophile, so a curly arrow going from the centre of the lone pair towards the partially positive carbon. Now obviously carbon now has bonded to 5 things, so that's not going to work, so the bromine leaves, this bond here breaks and the bromine leaves. So far pretty standard, nothing different. So again, standard, bromine leaves, there's the bromide with its lone pair of electrons that come from that double bond. It's got a negative charge because it's gained one from carbon. And here is the ammonia molecule joined onto the carbon, forming the this complex here. Now you'll notice that ammonia has 4 bonds, it's bonded to 4 things, and it's formed a dative covalent bond. So it's actually given one of its electrons to carbon. So this actually has a positive charge. So we'll give it a positive charge. So this is actually an unstable intermediate, and because it's got this positive charge, this actually breaks down, and eventually we're going to end up with this, the ethylamine. So it happens in another step. So this is why this mechanism is more complex. The way it happens is like this. The second ammonia, so notice how we had 2 ammonias, the second ammonia comes along and it acts as a base and forms a bond to this hydrogen. Now hydrogen can only be bonded to one thing. So when the nitrogen forms a bond with this hydrogen, this bond here has to break. And this bond breaks and both the electrons go towards this nitrogen. So a nitrogen, this bond is made from 2 electrons, one from nitrogen, one from hydrogen. Nitrogen is effectively gaining its own electron plus one from hydrogen. So that one from hydrogen will negate that positive charge. It will cancel out that positive charge. So this bond here is broken now, so this hydrogen is no longer attached to this nitrogen. This hydrogen is actually now attached to this nitrogen with these 3 other hydrogens. So you can see that's going to form our ammonium. And you can see once that bond's broken, it's going to form our ethylamine. So let's draw our final products in the displayed formula like we got here. So we can see what's formed. So that's what we just did. Down here is what's formed. So we got the hydrogens left. So it's only got 2 hydrogens now attached to it. That hydrogen joined onto that nitrogen. So we've got ammonium formed down here, positive charge. We've got the bromide ion, nothing happened between those 2 stages. This is our final product, our ethylamine. Okay, and this is the new, more complex nucleophilic substitution. This always occurs when you have ammonia.